All right. So I'll be talking about the relationship between heuristics, decision procedures, and Bayesian inference. So normally we think about heuristics as rules of thumb, imperfect approximations to what we should do. So rather than appropriately weighting all the information, some information gets neglected in heuristic decision procedures. So this is the kind of classic Kahneman and Tversky heuristics and biases program characterization. And so heuristics work most of the time, but sometimes they, if you design a clever experiment, put someone in an unusual situation, they'll fail spectacularly. More recently there's other manifestations where the simplicity of heuristics is seen as a virtue. So this is kind of more in the ecological rationality Gigerenzer view of heuristics, where neglecting information could actually make them more robust decision procedures. But no matter what the characterization of heuristics is, they're always contrasted with Bayesian inference, or really any decision procedure that fully weighs and integrates all the available information. And so what I'm going to do today is suggest that heuristics are actually a limiting case of Bayesian inference when one has a very strong prior. So this is going to be just a formal high-level computational result, and if there's time I'll get more into what this means for psychology and unpacking what's more at the algorithmic level, what's going on with heuristics. But before doing all that, I'll just say a little bit what heuristics are and what Bayesian inference is. Okay, so again, heuristics don't always work, but usually do. So this might be like your IT reboot heuristic. Okay, so it's not really what you should do maybe all the time. So this is more like kind of the Kahneman heuristics and biases reboot, but it generally works. And if you took the other perspective, you'd say, well, this isn't amazing. This would be sort of the Gigerenzer perspective. This is our evolutionary environment, maybe where this heuristic developed, and it's robust across situations. But either way, it's not a full integration of the information that's going on. So I guess as an undergraduate, I first came across this idea that I guess I didn't really need psychologists to tell me that people aren't rational and in a simple sense aren't Bayesian. And so let me read this vignette from Kahneman Tversky's paper on base rate neglect, which you could really see as prior neglect. Okay, and the idea here is again that people aren't fully integrating all available information sources. So, okay, let's look at the example of courtroom testimony. There's been a hit-and-run accident at night involving a taxi cab. The only eyewitness identified the taxi cab as being blue. There are two taxi cab companies operating in the city. One company has green cabs, which make up 85% of the total cabs in the city. The other company has blue cabs, which make up the remaining 15%. The eyewitness testified in court under similar nighttime conditions and was able to accurately distinguish the color of the cab 80% of the time. What is the likelihood that the eyewitness correctly identified the cab as blue? So most people will give an answer to this like a little below 80%. So you could think of here as the base rates. We have the more common cab, the green one 85% of the time is the prior before you have any observation. So if you didn't know anything and you knew there's an accident, you would probably say there's like an 85% chance it was the green one. And you could think of the observation, the likelihood as like being this 80% thing. And so what you should do if you're a Bayesian is multiply these two pieces of information together. So I guess the evidence for the blue one would be the 15%, the prior times the 80%. And if you did it for the green one, for the relative evidence for that, you would multiply the 85 times now the 20, and you actually get a higher number for the green one. But no one does this. Everyone thinks it's the blue cab. And so with heuristics, what you get is that you usually focus on the cues that predict something. So there, the neglect or the lack of integration involves how things are selectively weighted. So let me just go through an example that I'll consider later about the tallying heuristic. So let's say you want to make a prediction whether Germany or England's going to win a football match. And so you might have a number of cues or predictors like league position, last game result, and so on. And what the tallying heuristic will do is we'll just compare the two options on each of these cues and we'll put a smiley face if it's better, so Germany has a better league position, Germany and England tie on last game result, England's better on home versus away record. And so we could just code that, because later we'll set this up as a regression problem, where if Germany's better, it's +1, if they're tied, it's a 0, if England's better, it's a -1, and so on. But what it comes down to is just basically count up the smiley faces, add them up, and whoever has more smiley faces, that's the prediction of tallying. So a lot of information is being discarded here, because some of these predictors might be better than others. There could be covariance structure amongst the predictors. So two predictors, two Qs might essentially tell you the same thing, but they're going to be counted twice. So complete neglect of a lot of information, but this is sort of in keeping with how heuristics work. So it seems simplistic, but if you look at real-world decision procedures, so I just looked up DSM-5 last night, and if you look at a major part of making a decision, like whether someone has major depressive disorder, is just really counting up the smiley faces, or in this case, sad faces. So if you have 5 out of 9 of these, negative symptoms, then you could be, diagnosed as having major depressive disorder. A lot of tests work like this. So you might, the Montreal Cognitive Assessment, MOCA, has been used lately, and it's a bunch of simple questions, and you add up the points. So, you'd have to literally be a genius to get this right. You see this, you have to say, this is a lion. But the point is that you just add up the points. They're not weighted or anything. So yeah, of course, this is coming. So, there's been a lot of worries about the sanity of the U.S. president. Of course, he's a genius, a stable genius, mastering the hand-shaking game. And of course, he got elected the first time, not a lie at all, the first try of running for president. But yeah, but we put faith in these things. He's probably ruined the MOCA for clinicians everywhere, because now everyone will be looking up the answers to this test. But to get serious again, these heuristics are used everywhere. So in forecasting domains, you might use really sophisticated investment models, but what economists recommend, what tends to work well, is just this 1/n rule. So it's almost like a diversity heuristic where n is the number of asset classes, and you just spread the money, the investment evenly. So if you had utilities, large market cap corporations, or currencies, you just spread the money evenly. It seems very simplistic. It seems like it's neglecting a lot of information, but in practice, these kind of heuristics work well, and to the point that again, some people like Igor said, this is robust, this is what you should do. They should, simple is better. You should neglect the information. This works better than Bayesian inference. But again, what I want to argue or to show, it's not really an argument because it's formal proof, it's just that that you could actually see these heuristics as a type of Bayesian inference. And so that has an implication, not just, not just things are Bayesian, they're better or something, but more that why do these heuristics work? Is it because of their simplicity? Like maybe at an algorithmic level, they're easier, just to do in your head than doing some complex integration. No, that's saying that's not why they work. Ignoring information is really never an optimal thing to do. You should always appropriately downweight information. Instead, these heuristics work because they, embody like a probabilistic model of prior that is close enough to the environment that it does decently. Okay, and so you can see, while these heuristics are taking off, there's all this work, more on the Bayesian end of things, often more in perceptual motor integration. Here's one popular example. But in the last couple of decades, it's been going on more at a higher cognitive level as well. So, with collaborators like Benedetto De Martino, even I've gotten on this act. So here's an example of how people might integrate things on Amazon. So these are just the materials from Amazon. So in the initial phase of the experiment, someone would be shown a product, and they'd say, just like on Amazon, how much they like it, and they would give a confidence rating as well. And then in the fMRI scanner in the second part of the experiment, they would give a rating again now, but in the context of other people's ratings. So here you can see, people like this a little bit more than the person, and there's, 132 people rated this. So if someone were Bayesian, what should happen is you should move this is like your prior, and you should move towards these observations towards the other people because they're providing you with some information about the product. And so how much you should move if you're Bayesian is, if you're not very confident here, you should move more. If you're very confident, you shouldn't move very much. So if your prior is strong, you should move a lot. And conversely, you should move more towards the group when the group's larger. It's sort of like more evidence. You shouldn't move a lot maybe if it's just one person. So people show that qualitative signature. And so again, this is sort of like the more sophisticated version of the Kahneman and Tversky. You start off with some beliefs. You could think of it that way. And then here are the other people's beliefs. And you move towards it to have some posterior final beliefs. So that's like if you appropriately integrated all you knew and weighted things correctly. If you look at how much update happens from your prior beliefs to your end belief, we talked about all these confidence areas in the brain. There's this area in dorsal medial prefrontal cortex that does a good job of tracking that update process. So I mean, this looks like, well, does this mean your brain is Bayesian or we're Bayesian behaviorally? Well, I'm not sure in a real simple sense that's true. There's usually a lot of daylight between the models if they're set up to do, actually the best thing, what they should do in the task, versus what people actually do. But at the same time, there's these qualitative trends that are consistent with these Bayesian models. So to go all the way back to the base rate neglect example from Kahneman and Tversky, it's not like people completely ignore the base rate. To use the experiment I just showed you as an example, people are a bit noisy. They might not do exactly the right thing, but they do show sensitivity to how many people, rated the product at Amazon. So they do show some sensitivity to the evidence. They do update more when they're lower confidence in their initial assessments and when their prior is weaker. So, perhaps we really shouldn't be setting this up as a dichotomy between, sort of Bayesian, rational, doing things optimally, and versus like these heuristics that are very simple and they discard information, perhaps, out of hand as opposed to doing some downweighting. Maybe people are doing, I don't want to say something in between because it's going to end up being, suggesting a computational level of Bayesian account, but maybe these two extremes can actually exist on a continuum, and there's intermediate solutions that would perform the best and perhaps even characterize what people do. Okay, so I'm going to return to this example and a couple heuristics and show how they're limiting cases of kind of a proper Bayesian model when the prior is very strong. So I've already explained the tallying heuristic, which basically just counts up the smiley faces for each option, and whoever has more smiley faces, that becomes the choice. So in this case, tallying would pick England because it bests Germany on 2 of the 4 Qs, whereas Germany only bests England on 1. Another popular heuristic is the take the best heuristic. According to this heuristic, the Qs are ordered, so it's more of a sequential process. So the Qs are ordered by something called Q validity, which is just how well does a Q predict in isolation. So if you only knew that one Q and nothing else, nothing about the covariance structure, how well could you do? And so here are the Qs in this fictitious example ordered by Q validity. So if you only knew one thing, and had to make a prediction who will win the game match, it should be league position, whereas number of goals would be, this is Q validity, would be the least valuable single piece of information. No. So what take the best does is it starts with the top Q with the highest validity, and if the Q favors one option over the other, it just chooses that option and terminates. And if there's a tie, then it goes on to the next Q and so on. So you could see how take the best really could discard a lot of information. It might just use one Q. At least it is using some kind of preference ordering, not really a weighting. But both these heuristics neglect a lot of information, which you could contrast with just say linear regression, which I'm just using here because in this literature it's used as a foil for the sort of rational way of integrating things. Linear regression is very simple itself, but it actually takes into account a lot more information than these heuristics. Linear regression, looks at all the Qs, unlike take the best, and it weights them unlike tallying, and it just doesn't weight them by the Q validity. So we all use linear regression, but a lot of people don't appreciate that it's taking into account the covariance structure of the Qs. You know, so if you put in, it's like if you have 2 copies of a newspaper from the same issue, you don't treat that as 2 pieces of information, right? Because they're perfectly correlated. So linear regression does that. It takes into account the covariance structure. So like some of these Qs might correlate with one another, and it'll take that into account. Okay, but despite that, so the reason like a lot of people got excited about the heuristics work early on was that despite the simplicity of the heuristics, or perhaps as the aficionados argue for, because of the simplicity, these heuristics can best regression. So here is showing the fit of regression model and these 2 heuristics to 20 real-world data sets that involve predicting things like house prices and so on. And you can see that regression in yellow here, yellowish here, fits the best, okay, on the training data. But if you look at generalization performance on held out data, so you could think of it as like a cross-validation procedure, so novel data hasn't seen, the heuristics and the way they set up this training test set split actually do a little bit better. So this is sort of arguing for this less or more, that somehow ignoring information is better. And that just doesn't seem correct. It doesn't seem like closing your eyes is a useful way of making decisions, but nevertheless it's working better here. So what's going on? You know, so one common explanation for this is you could appeal to a concept actually like more from a frequentist viewpoint of bias-variance trade-off. So if you have models, which these are, you could think of them as existing on an axis of complexity. So you could have more flexible models like regression out here, and more constrained, perhaps simpler models like heuristics on that end. And as you increase model complexity, so you move this direction, the fit, so how well you'll fit the training data, will always increase, you know, as you add parameters. Parameters should help you. But you might start fitting the idiosyncrasies, you know, you might overfit, you might fit the idiosyncrasies, the variance in your training set, and pick up on things that aren't true. So that will actually start reducing how well you'll generalize the novel data. So this is like one, you know, possibility of what's going on with these examples where heuristics do better. And so we replicated these kind of findings ourselves. And of course, the data itself matters, so the sample size of data will matter. Simple models do better with when there's less data. More complex models do better when there's more data. And so you can see here, the heuristic, take the best, does better than regression, but when you have larger data set, it's not true. Okay, so one way to deal with this sort of overfitting issues that people use in regression, I'm going to use this to build up to the Bayesian account, is penalized regressions. So regularized regressions is another way they're calling. So you might have come across ridge regression, and it basically has 2 parts. The first part everyone will be familiar with. It's sort of just the fit term. So this would just be like a regular regression. If you just had this, it's just looking at the Qs. Sorry, it's hard to see. These X of I's are just like, you know, the league position. These are the predictors, and you weight them in a regression, and then you just see, well, what's the squared error, you know, and just minimize that. Find the weights that minimize that. So what these penalized regressions do is they include a second term, so penalty, that in this case it's just you square the weights. So this model will, all things being equal, prefer models with smaller weights, right? So it's basically putting in this prior that the weights should be small, and so, you know, you have to observe something pretty extraordinary to have really big weights, because you pay a price here, and the stronger, you could think of it as your prior, the bigger, you know, this parameter would be here, okay, to enforce it. So that's a way of navigating this model flexibility continuum in a regression framework. And so you could think of all these kind of models. This is what I'll try to show, that the heuristics, regression approaches, Bayesian approaches as relating to one another. And so what I've basically shown you here is this little bit here with the ridge regression. And of course, if you take out this kind of prior strength, you'll get back regular regression. But it turns out, you could go upwards too. Instead of just thinking of the argmax, the kind of the best weight, if you think of the whole distribution of weights, well, then you'll end up with like a full Bayesian model with, a Gaussian prior and likelihood. And so this isn't novel. So this is not something that, we've come up with. But what I want to do that is a bit new is kind of move down this branch to include heuristics. So you could make a variant of this full Bayesian model starting up top that is like the original formulation of the tallying heuristic, where you assume people know the valence of the cubes. So scoring more goals is better. If you're looking for an apartment, a flat, usually bigger is better, or a better view is better. So if you do predetermined Q locations, it's like basically using half a Gaussian, and we call that the half-bridge model. And through it's a tedious proof. This is published. You can look at it. But if you crank up the prior in this Bayesian model and make it very strong, the weights and the variances will race, towards zero, but they'll kind of stabilize at this. You really can't. It doesn't matter, but they'll stabilize basically at a constant. So you'll get back tallying. So it's kind of neat. So it's basically showing that tallying is, a limiting case of this Bayesian model where you have really strong prior expectations. So in this case, it just quashes caring about selectively weighting things. Okay, but of course so that's basically already kind of showing, just formally, if you want to go through like 2 pages of Matt Jones's brilliant derivations, that you could, these heuristic, this is the case of a heuristic just being a limiting case of a Bayesian model. But maybe more interesting to me is that, what about these intermediate cases? So there's a lot of little plots here. These are a bunch of real-world data sets, the same ones that the heuristics folks tend to use. So they're predicting things like mortality rates, home prices. On this side, the prior is really weak of each graph. On this side, it's really strong. So on the left of each one of these plots would correspond to this strange linear regression where you kind of already know the valences of the Qs. On this end would correspond to the tallying heuristic. And what you might be able to make out is usually the sweet spot is somewhere in the middle. So you can see it strongly here on this mortality rate one here. So, it's not less is more. So closing one's eyes is not beneficial. If you just do some down weighting, but not just completely treat every Q as the same, you do some weighting, you could almost always do a bit better. Okay. So far I've gone through connected tallying where we already know the Q valences into a Bayesian model. But what about take the best? Also, what about tallying where we have to learn the Q valences? We have to learn whether some Q indicates something good or something bad. So to do that, I had to trot out a new model. It's a bit of a contrivance to deal with the sequential nature of take the best, because if you remember take the best, you first look at one Q, and if you find it distinguishes between the options, you just stop there. But if not, you go to the next one. That actually was kind of hard to crank through this analysis. So we made this model. It's kind of this network where you have as many. If you have 3 predictors, like 3 Qs, you'll just kind of clone the output variable. So if this is Germany or England won the game, you just put the same result 3 times. And the way we set it up this way was, because when we're going to do this sort of prior, this sort of kind of penalization of weights, we're only going to do it for these diagonal weights that don't go directly to the kind of cloned outcome variable above them. And because these weights carry the covariance information, and so what will happen is if there's the prior is very diffuse, so you could think of this as like no penalty, you'll just get back like a multivariate linear regression. Basically just get back linear regression. But if you make the prior very strong, you'll just get these direct weights, okay, from a Q to the outcome. And so that's basically, you could show that's equivalent to Q validity. So that's just basically, how well do these Qs predict in isolation. So you could think of this, if you think of these weights as like the knowledge of the model, Here it's like the knowledge of a linear regression one. Here it's sort of the knowledge of the heuristic one. And now to get to a decision, we have to add something on top. So we have these decision procedures we put up on top. So we have a tallying decision rule, which just takes these outputs, these y's, and just adds up their signs. Okay, so it's like a voting procedure again, just like adding up the smiley faces. But it's not exactly tallying itself unless the prior is really strong. If the prior is not like extreme, you can't actually have sign flips. So in linear regression, even if you have a predictor that alone, say, has a positive weight, if you put it in the context of other predictors, it could actually flip negative because of the covariance. So, but anyway, this is a tallying decision rule, and we have a take the best decision rule that just takes the output here that's the largest in absolute terms and bases the decision on that. Okay, so if you again, at the extreme, you'll get take the best out of this, but for intermediate solutions, it might diverge a bit. Here's just showing that this model with the take the best decision rule will converge to take the best. So as you make the prior stronger and stronger, this is the agreement of this Bayesian model with the take the best heuristic. At first, it's not that high, but as you make the prior more extreme, it reaches 100% agreement with take the best across a variety of data sets. And this is just showing the opposite relationship for regular, regression. At first, it agrees, perfectly with regression. So you can think of regression as just having a really weak prior. And as you increase it, it goes down. And here's the same thing for the tallying decision rule. So this is the same model, just using a different decision procedure on top. You can see, it's a little bit like tallying with a weak prior, but it becomes more so and eventually converges to 100% as the prior becomes, really strong. Okay, and once again, I'll just show you the intermediate solutions. You don't have to look through these all, but the key point, this is the core model with the tallying decision rule. The key point is that these intermediate models that don't completely neglect information, that aren't going, just closing their eyes like the heuristics, tend to do better. So especially for the smaller data sets are shown in red, smaller training samples, and then you have a little bit more data. But in each case, you can see there's a bump for the intermediate model. So this is just showing the sort of strong Gigerenzer like less is more characterization doesn't really hold, that when you put these models on a continuum and appropriately have appropriate prior, you could always do like a little bit better. So closing your eyes is not what you should do when you're making a decision. Okay, and here's for the take the best decision rule. Same idea. The intermediate model with the medium strength prior tends to do the best. So, here's like your pure regression model. Here's your like pure heuristic, take the best. And you could do a little better in general by not closing your eyes like the heuristic, but doing some appropriate prior, unlike linear regression. Okay, so you can see there's not Wi-Fi in this room, so I'm very bad. I was going to make a new slide here to show you some new results. But with Matt Jones, we tried to think, can you do this the other way around? So we already knew about linear regression and take the best and tallying. Can we take a Bayesian model, like sort of a quote-unquote rational model, and turn the crank by making the prior really strong? Can we actually invent new heuristics and, or at least recover, something existing? I wouldn't be surprised if this already existed, something already existed. So we took a popular, this is work that's not yet published. We took Gaussian process regression, which is a little bit more complex. It's a Bayesian regression. It's more complex than regular regression because you could have things that show more complex patterns, and it's like a robust and popular way to analyze data. And we did a couple limits. And one limit, interestingly, is you increase the prior on one of the parameters in Gaussian process regression. You actually get out a psychological model, that the generalized context model, which is Nosofsky's exemplar model. It's a model that people make decisions by individual traces of memories, and they're all co-activated. And so the GCM, I never really thought about it as neglecting information relative to Gaussian process model, but it does, just like these heuristics do. And if you do another limit, you actually get an even simpler exemplar model. It's the nearest neighbor model. So that's like if you're trying to predict something about something, you just retrieve from memory whatever is the most similar thing to that you've encountered before, and you use that to make your prediction. So if you're like, how good is this person at tennis? You'll be like, who's the most similar person I know? Okay, they're going to be that good, exactly. So this looks like it might be a general phenomena that if you boost the prior, make it really strong, and you'll end up with some kind of solution that's simpler at an algorithmic level, maybe a little bit more psychologically plausible, definitely easier to like implement in your head. Okay, so some conclusions here are you could see heuristics as opposed to not being diametrically opposed as with Kahneman, Tversky, and Gigerenzer, describe them, not being diametrically opposed to Bayesian inference, but actually Bayesian inference themselves. They're just limiting cases in which the prior becomes infinitely strong. You end up with these heuristics. So, maybe people do adopt strong priors in situations, and maybe these are more robust. So it's not necessarily contradicting things that Gigerenzer and colleagues have said, just that, less is not more. And this is maybe not a surprise to more computational people that, or just, closing your eyes is not always helpful. So, heuristics, again, they might stick around. They might actually be used psychologically because in cases, they do have a lower, cognitive. You could think of it as algorithmic complexity. So, for example, this procedure hasn't always worked well in practice with tragic consequences, but this is a kind of a fast and frugal decision chart given to soldiers manning checkpoints, and you're supposed to check for certain things, and if they're satisfied, then don't shoot. Otherwise, shoot, because it could be a suicide bomber or something. And you could imagine someone coming up with this because you have to make a decision fairly quickly in the situation, and maybe these like complex integration processes are too much to handle. See, in the interest of time, I'll just really briefly say a little bit about a follow-up line of work that we've done that is not as purely formal. So everything I've shown you so far are really like proofs and simulations about how heuristics and Bayesian models work. But once you start thinking in terms of these ways, in terms of more algorithmic complexity, you're really getting into the psychology of how people represent information, process information, and what kind of cognitive processes are engaged. And strangely, that's actually really neglected in the heuristics literature. So heuristics themselves are often treated as these monolith conceptions where there's just like fast and frugal. And when we run studies, we've seen that heuristics are often fast or frugal, but not both. Just to give you a little, I'll just go through this very briefly. So in these studies, we showed how the information format could really affect which heuristic works best. So you could really tease apart even individual heuristics like tallying and take the best by how you set up the problem. And these are real experiments with hundreds of people, but they're almost like thought experiments. Like, I'm not sure we actually had to run them. So if you set up something where you color code things like the good cue, the smiley face is green, the inferior thing is in red. So this is for predicting which country will have higher GDP growth. And you make it, that's really easy for tallying because you could almost do this perceptual summation, right? And you could see there's more green stuff over here than over here. So it's really easy if you're using tallying to say, oh, I should choose country B. On the other hand, if you're doing take the best, and we did this made it impossible for take the best by randomizing the order of these cues with their presentation across trials, it's a really difficult sequential search procedure, right? First you have to find the best cue, then you have to check it, and if it's equal to the next one, and so on. And so in this case, if you set up the experiment that way, under time pressure or no time pressure, tallying, of course, is unaffected by the time pressure in red here, whereas take the best, craters. Okay, and that's just because it takes forever when you're not under time pressure to do take the best under these conditions. And you could do model fits and see that the reason is that when you're not under time pressure, when you're doing take the best, you integrate like, 3 cues. You go up to 3 cues in the decision if there's a tie. But when you're under time pressure, the red bars, sometimes you only just could consider 1 cue, and if there's a tie there, then you're just going to be wrong. But of course, you could flip this around really briefly. So you could make a nightmare experiment for tallying. So you could make everything now black and white, so you can't do this perceptual integration. You could order the Qs by their Q validity, so the best one's always on top. And if you run the experiment this way, the same information structure in the environment, you get the opposite results. So now tallying craters under time pressure, okay? So the point of this really is just that once we get into this realm of sort of the psychology, not just the formal relationship of these things, there's been precious little work on like unpacking what actual cognitive processes are involved with these heuristics, and this is going to involve stimulus formats, how it's going to affect search procedures, and that's going to be part of the understanding. So if you're going to push heuristics as having value in decision sciences, it's given that they're not. I think we make a good case that they're not special at a computational level. You're going to have to get into more of the psychology of what's actually going on in processing. So a little bit more work will be needed there. Okay, so to wrap it up, you can see heuristics as a limiting case of Bayesian inference. And so it might not be sensible to debate whether someone is using a heuristic or being Bayesian, given that heuristics appear to be limiting cases of Bayesian analysis where you have a strong prior. And this is important to understanding why they work. So they don't work because they ignore information. They work in spite of ignoring information. They work because they're embodying a prior that is somewhat aligned with the task, but not perfectly aligned. As you saw in the simulations, if you use an intermediate prior strength, you could always do a little bit better. So if you don't close your eyes, you could always do a little bit better. So perhaps this is consistent with the idea that people do adopt strong priors if they're looking more heuristic-like in their behavior. But maybe heuristics, I think the action could be more at the algorithmic, more at the sort of cognitive level, because you can come up with heuristic accounts that have lower algorithmic complexity. So I gave you this one example from recent work. Instead of doing this complex Gaussian process regression, you could literally do nearest neighbor, like what does this remind me of? And base your decision on that, and that's kind of a limiting case of Gaussian process regression. So that's going to involve, as I flew through in the last part of the study, of unpacking the psychological processes and representations that are used when people engage in some kind of, if you want to call it, heuristic decision procedure. Okay, so I'll stop there, and thank you.
Thank you. I was curious about the mathematical formulation of the half-bridge. That's the first thing. And the second is, can you evaluate the energy that is gained by heuristic, and is it the best taking into account the energy? And maybe a third thing is that sometimes you don't know the probabilities that you can sum when you integrate the Bayesian. So when you don't know the probabilities, maybe heuristics are better.
Oh yeah, no, these are all great points. So half-bridge, I'll just very conceptually, it's just like truncating the negative half of the distribution. Because to go back, so in the original formulation of the tallying heuristic, it's like you kind of know the valence of the Q, so like a bigger apartment's better. So to build that into the model, you just have to basically cut off half the weights, so like only the positive weights. In terms of the proofs, like they're online and it's hairy, but they work, and I should also say they're general too. So it's not just about L2 regularization for the squared weights. If you do like a Laplacian prior, you'll get the same. I'm sorry, what's up? Actually, I should go on to the second and third question. But I think the second question was about energy. I mean, I'm not sure. Maybe we should talk a little bit about that online. But it seems like a concept that would involve, some physical instantiation of it. I mean, maybe are we I don't know if we could do like a free energy version of these models or something, but. Yeah, so I mean, that could be something. I think it gets a little bit to the last part of the talk. This might not be how you intended the question, But when you have something that has resource limitations or certain kind of operations are more costly than others, then there might be a sense in which you would want to give something up in terms of performance because of the cost of like doing the computation. And to get to your last point, yeah, it's a really good point. So the last point you made was that all these probabilistic models rely on, yes, they're great for dealing with uncertainty, but they're not dealing with like kind of the unknown unknowns in the Donald Rumsfeld speak. They're dealing with when you kind of know the probabilities of things. And so it might very well be that if you don't have the probabilities, that the heuristics aren't horrible. Although what we saw from at least all these simulations we did, that if you downweight a lot, so you don't completely ignore information like the heuristics do, you could almost do a little bit better in every case. So what I suspect is if you take a combination of whatever all you're saying, it's probably true. So it's probably that like you don't want to downweight completely, ignore things even if you don't know the probabilities. I don't think. You probably want to have a strong prior, probably not as strong as the heuristics. But then there might be situations, what you said about the energy, the cost. It might just be that it's not worth the gain you get for people to take into account weighting all these things. You might be better off just practically to ignore them. But I don't think that takes away from the results they're showing, because they're really just showing why do these things actually work. There's nothing magical about less is more effects. You could understand them by bias variance trade-off. You could understand them in terms of Bayesian inference. And so you should always downweight if you can. And I don't know. Anyway.
Yeah, so this is a very naive question. The different data sets that you analyze, they have a number of predictors. I wonder if you find something particular in this set of predictors, that are available for these data sets, in terms of the covariance structure, for instance, and if there is a general notion that basically we happen to be able to predict these different variables because we have discovered the different predictors, and the way we discovered them was maybe because one was first discovered and then some others were correlated with the first one, and so in general, like these are particular data sets, but how would it happen in a more general case in which you may have just one predictor and then may be able to discover the other predicting variables?
Yeah, no, it's really interesting question. So it's almost like I guess what like computer scientists would call like this feature discovery problem or feature selection. So models don't really have a lot to say about it. So like the way things generally work is like these spaces are really high dimensional. So practically like a lot of the feature discovery ones, they should ideally take into account covariance, but many actual systems just grab predictors like the heuristics, just like what works well in isolation. But you could imagine maybe refining that over time and maybe kicking out predictors that don't really add a lot of independent information. I mean, that'd be a really interesting question as to like how effectively people do this. It could even affect which decision procedure you use. So Paula Parpert, the first author on those proofs, that proof paper in the middle, has done some work looking at so basically take the best tends to work better when there's tons of covariance. And it makes sense because tallying just adds things up, and you don't want to really add up redundant information and treat it like it's not redundant. But anyway, yeah, there's a host of really interesting issues that I think the field's neglecting that you're highlighting in your question. Yeah.
Just the last question. So I was wondering where in this model is there room for variance in the way the decision maker makes this regression or anything, place where the model might be intrinsically variable. Because if you imagine that humans have this variability in the way they combine the cues, so even if you present them twice with the same input, they would generate variability, there would be randomness or variability in their internal variables. And then if it is the case, which I expect it is, then wouldn't these strong priors have the benefit for the decision maker to be more self-consistent? And that maybe they would have these strong priors because due to the fact that they know that they have internal variability in the way they process things, that having strong priors would make them more self-consistent.
Yeah, I think that's a really good idea. So the second part of the talk with these models, they're completely formal. There's really, I mean, there's not really actually psychology there, right? It's really just like, how does this stuff relate to each other formally? Why does it work? And only in the last part of the talk was there some psychology. Yeah, I'm a big fan. I think a lot of variability in behavior comes from how we sample memory. And it might even relate to the previous question. And the first question, maybe, you have to add another, if you want to make it Bayesian, maybe you need another layer on this of the uncertainty over the uncertainties, what's going on. And you might find that like a good compromise ends up pushing the priors more extreme. And again, we had questions about like algorithmic complexity or energy, so maybe you just end up with there. But there's at the same time though, when I look at like recent behavioral analyses of comparing some stuff that I'm involved in myself, comparing whether people are using all the cues or doing something like take the best, like it looks like people do like, often rely on a little bit more information than these simple heuristics suggest. I mean, it's complex to evaluate and it's going to depend on the study setup, but but I guess I always think of decisions being made more from like retrieving things from memory, so I guess that's what you would get. You would get some sensitivity to many information sources, unlike the heuristics, but you would get what you're saying too. You would get, increased variability.